Tonight, we're going to explore the greatest unsolved mystery in the history of physics. A mystery hiding in plain sight for nearly a century. A mystery so vast that it makes up 27% of everything that exists, yet has never once been directly detected, never touched, never photographed, never captured in a detector, never produced in a particle accelerator. We have known for decades that it is there. We can measure its effects on every galaxy in the observable universe, and we have no idea what it is. Dark matter is not a theory. It is an observation. Every measurement ever made of the large-scale structure of the universe points to the same conclusion. Most of the mass in the cosmos is invisible. There is roughly 6 times more of it than the matter that makes up everything you can see. Every star, every planet, every atom of gas between the galaxies, every particle of dust, every human being who has ever lived. All of that visible matter is a thin coating on top of a vast, invisible scaffolding that holds the universe together. A scaffolding we cannot see, cannot touch, and cannot explain. This is not a fringe idea. It is not speculation. It is as well established as the existence of the planets. The evidence comes from dozens of completely independent lines of observation, using completely different instruments, measuring completely different phenomena, all converging on the same answer. Something is there, something massive, something invisible, and after 100 years of the sharpest scientific minds on Earth devoting their careers to finding it, we have found nothing. By the end of tonight, you're going to understand exactly what dark matter is. You're going to understand how Fritz Zwicky noticed something wrong in 1933 and was dismissed and ignored for 40 years until a woman named Vera Rubin proved him right so conclusively that no one could argue anymore. You're going to understand what dark matter does, how it built every galaxy that exists, how it shaped the cosmic web that organizes the universe on the largest scales, how it is passing through your body right now at a rate of billions of particles per second. You're going to understand every candidate, the WIMPs, the axions, the sterile neutrinos, the primordial black holes, and why every single experiment designed to find them has come back empty. You're going to understand what happens to galaxies without dark matter, what the bullet cluster proved beyond all doubt, and why the mystery is, if anything, getting deeper the harder we look. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The story of dark matter begins with a problem that should not exist. A straightforward calculation. A measurement that, if the universe were behaving the way it was supposed to, should have given one answer and gave another. In 1933, a Swiss-American astronomer named Fritz Zwicky was sitting in an observatory in Pasadena, California, staring at data from the Coma galaxy cluster. The Coma cluster is a collection of roughly 1,000 galaxies gravitationally bound together, sitting about 320 million light-years from Earth. Zwicky was measuring how fast the individual galaxies were moving within the cluster. He could do this because when a galaxy moves away from us, its light is redshifted, stretched toward longer wavelengths, and when it moves toward us, its light is blue shifted. The degree of shift tells you the speed. What he found was that the galaxies in the Coma cluster were moving much too fast. To understand why this was a problem, you need to understand the physics of a gravitationally bound system. A galaxy cluster is held together by gravity. The galaxies orbit the cluster's center of mass the same way planets orbit the sun. The faster an object moves in an orbit, the more gravity is required to keep it in that orbit. Too much speed, and the object escapes. The cluster should fly apart if the galaxies are moving faster than the escape velocity. And in the coma cluster, they were moving much faster than the visible mass could account for. Zwicky did the calculation. To keep the cluster together, to provide enough gravity to hold those fast-moving galaxies in their orbits, the cluster would need roughly 400 times the mass of all the visible galaxies combined. Zwicky was not a modest man. He announced this immediately. He called the invisible mass Dunkel Materia, dark matter, and the response from the scientific community was, "Zwicky has made an error." Nobody took it seriously. For 40 years, the observations sat in the literature, occasionally cited, mostly ignored. The idea that most of the universe's mass was invisible and unknown was too radical, too uncomfortable, easier to assume the measurement was wrong. Then came Vera Rubin. Vera Rubin grew up in Washington, D.C., building telescopes from cardboard and watching the night sky from her bedroom window. She wanted to be an astronomer from the age of 10. She was told, repeatedly and in various ways by various institutions, that this was not a suitable ambition for a woman. Princeton's graduate astronomy program did not admit women. The University of Pennsylvania ignored her application. She got her PhD from Georgetown in 1954, one of the only women in a PhD program in astronomy in the United States. By the early 1960s, she was at the Carnegie Institution of Washington, and she had developed a specific interest in how galaxies rotate. This was not, at the time, considered a glamorous problem. Nobody expected galaxy rotation curves to produce anything surprising. The physics seemed straightforward. A galaxy is a collection of stars rotating around a common center. Stars closer to the center have more mass pulling them inward, and so orbit faster. Stars farther from the center have less mass pulling them, and so orbit slower. Just like the planets in our solar system, Mercury moves at 47 kilometers per second. Pluto moves at 4.7 kilometers per second. The outer objects always move slower. Rubin began measuring rotation curves for spiral galaxies with her colleague Kent Ford, using a spectrograph of exceptional sensitivity that Ford had built himself. They started with the Andromeda Galaxy, the great spiral 2.5 million light-years from Earth, the largest galaxy in the local group. They measured the velocities of stars and gas clouds at different distances from the galactic center. Then they graphed the results. The graph did not look like what physics predicted. The curve did not fall off. In a normal system, in a solar system following Keplerian dynamics, the velocity curve drops steeply as you move outward from the center. This is what everyone expected. Instead, Rubin found that the rotation velocity was roughly constant at all distances from the center. Stars in the outer reaches of Andromeda were moving just as fast as stars much closer in, sometimes faster. This should be impossible. If the only mass present is the visible mass, the stars and gas you can see, the gravity in the outer regions of a galaxy is not strong enough to keep those stars moving at those speeds. They should either be moving slower, or they should have escaped the galaxy entirely billions of years ago. Rubin repeated the measurement for other galaxies, then more galaxies, then dozens of galaxies. Then, by the early 1970s, over 60 galaxies of different types, sizes, and orientations. The result was the same every time. The rotation curves were flat. Not falling, flat. There was only one possible explanation consistent with Newtonian gravity and general relativity. There had to be additional mass in the outer regions of every galaxy. Mass that was not visible. Mass that extended far beyond the visible disk of stars and gas, in a spherical halo surrounding the galaxy, dense enough to provide the gravity that kept the outer stars in their fast orbits. The amount of invisible mass required was staggering. The visible stars and gas in a typical spiral galaxy, everything that shines, everything you can see in photographs, account for only about 15 to 20% of the galaxy's total mass. The other 80 to 85% is dark matter, invisible, unknown, but definitively present. When Rubin published these results in 1970, and then again more comprehensively in 1980, the scientific community could not dismiss them. She had not made Zwicky's mistake of working with a single cluster and producing a rough calculation. She had measured dozens of galaxies with extraordinary precision, using modern instrumentation, and had found the same result every time. The data was unambiguous. Still, there was resistance. Some astronomers proposed that Newtonian gravity must be wrong on galactic scales, that some modified version of gravity could explain the flat rotation curves without requiring invisible mass. This idea, called modified Newtonian dynamics, or MOND, was developed by physicist Mordechai Milgrom in 1983. It was clever. For individual galaxies, it worked reasonably well. But it struggled to explain the dynamics of galaxy clusters and could not account for other independent lines of evidence that were beginning to accumulate. Vera Rubin received many of the highest honors in science. She never won the Nobel Prize, despite the fact that most physicists considered her work on dark matter among the most important observational discoveries of the 20th century. The Nobel Prize is not awarded posthumously. She died in 2016 before the committee could rectify the omission. She is remembered as the scientist who proved that most of the universe is invisible, and who did so with a precision and persistence that left no room for doubt. But Rubin's rotation curves were only the beginning, as the evidence accumulated from entirely different directions, from galaxy clusters, from gravitational lensing, from the large-scale structure of the universe, from the cosmic microwave background. The picture became not just clearer, but more extraordinary. Dark matter was not just real, it was foundational. Without it, nothing in the universe would exist in its current form. To understand why dark matter is not just a strange footnote to galaxy physics, but the central character in the story of cosmic structure, you need to go back 13.8 billion years to a time when the universe was less than a second old. At that moment, the universe was a plasma, a soup of quarks and gluons and leptons and photons, all interacting violently in conditions of incomprehensible density and heat. The temperature was billions of degrees. There were no atoms, no nuclei, no recognizable particles, just a dense, furious, uniform fog. Almost uniform, not perfectly. The quantum fluctuations that drove inflation, the brief period of exponential expansion that occurred in the first tiny fraction of a second, had imprinted tiny density variations on this fog. Some regions were slightly denser than others, 1 part in 100,000, an extraordinarily small difference. But gravity is patient. A region that is 1 part in 100,000 denser than its surroundings has 1 part in 100,000 more gravity. Over time, that small advantage compounds. Denser regions attract slightly more matter. As they grow denser, their gravity grows stronger, attracting still more matter. positive feedback playing out over millions and then billions of years. This is how galaxies form. But there is a problem. In the early universe, normal matter, protons and neutrons and electrons, the stuff that makes atoms, is coupled to photons. When the universe is hot enough that atoms cannot form, electrons are free and they interact constantly with photons. This coupling means that normal matter cannot collapse freely under gravity. Every time a cloud of normal matter tries to collapse, the photons it is coupled to exert radiation pressure, pushing outward, resisting the collapse. The gravity pulls inward. The radiation pressure pushes outward. The net result is acoustic oscillations, sound waves in the plasma, rather than collapse into structure. Dark matter has no such problem. Dark matter does not interact with photons. It does not interact with the electromagnetic force at all. It feels gravity and possibly the weak nuclear force, and nothing else. So, when the early universe was full of hot plasma, coupling normal matter to photons and preventing collapse, dark matter was already collapsing freely. It was already forming halos, spherical concentrations of mass held together by their own gravity, growing denser and more massive, while normal matter was still bouncing around in radiation-coupled plasma. By the time the universe cooled enough for atoms to form, at about 380,000 years after the Big Bang, when electrons finally combined with protons and the photons were freed, dark matter had already built the scaffolding. The dark matter halos already existed. They were gravitational wells. And when the normal matter was finally freed from its coupling with radiation, it fell into those wells. This is why every galaxy in the observable universe is embedded in a dark matter halo. The halo came first. The halo created the conditions for the galaxy. Without the dark matter halo providing the gravitational well, the normal matter gas would never have concentrated enough to collapse into stars. The Milky Way's visible disk of stars, the 100,000 light-year spiral of 200 billion suns, sits at the center of a dark matter halo that extends at least 600,000 light-years in every direction and contains roughly 10 times the mass of all the visible stars and gas combined. You can see the disk. You cannot see the halo. But the halo is what made the disk possible. And this is not just the Milky Way. This is every galaxy that has ever existed. The cosmic web, the vast filamentary structure that organizes matter on the largest scales in the universe, with galaxies strung along filaments like beads on a wire, and vast empty voids between the filaments. That entire structure was shaped by dark matter. The filaments are dark matter filaments. The nodes where filaments intersect, forming the densest concentrations where the largest galaxy clusters sit, are dark matter nodes. Normal matter followed the dark matter. The visible universe is a faint tracing of the invisible dark matter skeleton that preceded it. Without dark matter, there would be no galaxies. Without galaxies, there would be no stars. Without stars, there would be no heavy elements. Without heavy elements, there would be no planets. Without planets, there would be no life. The thing we cannot see, cannot detect, cannot identify, the invisible unknown that makes up 27% of the universe, is the reason you exist. This is the first and most important thing to understand about dark matter. It is not a puzzle at the edges of physics. It is not a minor correction to an otherwise working model. It is the foundational structure of the universe. Everything else is built on top of it. By the late 1990s, the case for dark matter was overwhelming. Galaxy rotation curves, galaxy cluster dynamics, gravitational lensing. the large-scale structure of the cosmic web, the patterns in the cosmic microwave background radiation. All of these independent lines of evidence pointed to the same conclusion. But there was still a committed minority of scientists who believed that the problem might be solved by modifying our theory of gravity rather than by invoking invisible mass. Modified Newtonian dynamics and its more sophisticated successor, modified gravity, could explain individual galaxy rotation curves plausibly. And until 2006, the debate continued. Then came the bullet cluster. The bullet cluster, formerly known as 1E0657558, is what happens when two galaxy clusters collide. Galaxy clusters are the largest gravitationally bound structures in the universe. Collections of hundreds or thousands of galaxies held together by gravity and swimming in enormous halos of hot gas. The gas in a galaxy cluster typically outweighs all the stars in all the galaxies by a factor of roughly 5-to-1. When two clusters collide, the gas in each cluster interacts strongly with the gas in the other. It slows down, heats up, emits X-rays, and gets compressed into a characteristic bow shock shape. The galaxies, widely spaced within the cluster, mostly pass through each other like ghosts. What should happen to dark matter during a cluster collision depends entirely on what dark matter is. If dark matter is a particle that barely interacts with anything, which most dark matter models predict, then the dark matter halos should behave like the galaxies, passing through each other essentially unimpeded. The dark matter does not interact electromagnetically, so it does not slow down when the hot gas collides. If dark matter is some kind of modification of gravity, on the other hand, it should remain concentrated where the mass is, and the mass is mostly in the hot gas. So in a modified gravity scenario, after the collision, the gravitational effects you measure should be concentrated where the X-ray emitting gas is. These are clearly different predictions, and the bullet cluster makes it possible to test them directly. By 2006, astronomers had made 3 independent measurements of the bullet cluster system. First, they used the Chandra X-ray Observatory to map where the hot gas was. The gas was concentrated in the middle, between the two clusters, showing the classic bullet-shaped bow shock where the gas from the smaller subcluster had passed through the larger. This is exactly what you expect from gas that slows down and compresses during the collision. Second, they used optical telescopes to map where the galaxies were. The galaxies were offset from the gas. They had passed through the collision and were now ahead of the gas, on either side of the impact point. Third, and most crucially, they used gravitational lensing to map where the mass was. Gravitational lensing is the bending of light by gravity. The more mass in a region, the more it bends light from background sources. By measuring how distorted background galaxies appeared when seen through the bullet cluster system, the team could reconstruct a map of where the gravitational mass was located, regardless of whether that mass was visible or not. The result was unambiguous and dramatic. The mass, as revealed by gravitational lensing, was offset from the gas. The mass was not where the X-ray emitting hot gas was. The mass was where the galaxies were. In other words, most of the mass had passed through the collision without slowing down, just like the galaxies, while the gas had been slowed and compressed. This is exactly what you would expect if dark matter is a particle that barely interacts with anything. The dark matter halos passed through each other unimpeded, while the hot gas slowed down and was left behind. The mass and the visible matter became separated by the collision, and the separation is directly visible in the data. In any modified gravity model, The gravitational effects should follow the mass. The mass is mostly the hot gas, so the gravitational effects should be concentrated where the hot gas is. They are not. They are offset from the hot gas by several 100,000 light-years. The bullet cluster was the most direct evidence yet that dark matter is a genuine component of the universe. A substance, whatever it might be, that has mass and gravitational effects, but does not interact electromagnetically. It did not prove what dark matter is, but it proved, beyond any remaining doubt, that the dark matter problem is not a problem with our theory of gravity. Something real is there. Douglas Clow, who led the team that published the bullet cluster analysis in 2006, said it plainly. This result rules out any purely gravitational explanation for the missing mass. A gravitational modification cannot explain what we see. There is matter there. We just cannot see it. In the years since, many more galaxy cluster collisions have been studied with the same result. The mass always separates from the gas during a collision. The pattern is consistent and reproducible. The bullet cluster was not a fluke. Dark matter is real. What it is remains completely unknown. Let's try to make the scale of what we are dealing with concrete, because the numbers involved are difficult to comprehend without a frame of reference. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains, on average, somewhere around 100 billion stars. The total mass in all these stars is an enormous number, roughly 10 to the power of 53 kilograms. That is, a 1 followed by 53 zeros in kilograms. The most massive object most humans will encounter in their lifetime weighs a few thousand kilograms. The combined mass of all the stars in the observable universe is 10 billion trillion kilograms. There are no words in ordinary language for this number. Now here is the thing. That number, the mass of all the stars in the observable universe, represents about 1% of the total mass energy content of the universe. All the stars, every sun that has ever burned, in every galaxy that has ever formed, across 13.8 billion years of cosmic history. 1%. Normal matter, not just stars but all baryonic matter, including gas and dust and planets and you, makes up approximately 5%. Dark matter makes up 27%. Dark energy, the even more mysterious force driving the acceleration of the universe's expansion, makes up the remaining 68%. This means that if you somehow had the ability to take a census of everything that exists in the universe, every particle of matter, every form of energy, everything, 95% of it would be things we do not understand, have never detected, and have no confirmed theory for. The 5% that we do understand, that we have built physics and chemistry and biology and civilization out of, is a thin residue, a coating of known substance on a vast unknown substrate. Every time you look up at the night sky, every star you see is normal matter. Every photon of light that reaches your eyes is emitted by processes involving normal matter. The entire visible universe, the only thing human senses can ever directly perceive, is a small fraction of a small fraction of what is actually there. Dark matter is everywhere. It permeates every region of the universe. It is in this room right now. Billions of dark matter particles are passing through your body every second. Through the walls, through the floor, through the earth. They do not slow down because they do not interact electromagnetically. They do not deposit energy in your tissues. They flow through matter as if matter were not there. The only thing they feel is gravity. And on the scale of a human body, or a room, or a planet, Gravity is far too weak to make any measurable difference. Dark matter affects the universe on the scale of galaxies and galaxy clusters, where the cumulative gravitational effect of trillions of solar masses of invisible substance is decisive. On human scales, it is completely imperceptible. You are immersed in it right now. You cannot feel it. You cannot detect it with any sense or any instrument you have access to. It is there, passing through you, and it is as close to a ghost as physics has ever produced. The atoms in your body, and the atoms in everything you can see or touch, are the rare exception. Most of the matter in the universe is not this. Most of the matter in the universe is something else entirely, and we have no idea what. For 4 decades, the leading candidate for dark matter has been the weakly interacting massive particle, the WIMP. The name is a description of its hypothetical properties. It interacts only through gravity and the weak nuclear force, and it has mass. These properties emerge naturally from several theoretical frameworks beyond the standard model of particle physics, which is part of why WIMPs were taken so seriously for so long. The standard model of particle physics is the most precisely tested theory in the history of science. It describes the fundamental particles, quarks, leptons, force-carrying bosons, and their interactions with extraordinary accuracy. But physicists have known for decades that it is incomplete. It does not include gravity. It does not explain why particles have the masses they do. It does not account for the matter-antimatter asymmetry that allows the universe to contain matter at all. And it does not provide a dark matter candidate. Extensions of the standard model, however, do. Supersymmetry, a theoretical framework proposing that every particle in the standard model has a heavier superpartner, predicts the existence of stable, massive, weakly interacting particles as a natural consequence of its mathematics. The lightest supersymmetric particle, called the neutralino in many versions of the theory, would be stable, heavy, weakly interacting, and would have been produced in the right abundance in the early universe to account for exactly 27% of the universe's mass energy content today. This last point, the WIMP miracle, is what made WIMPs so compelling. Not only did theoretical physics independently produce a candidate particle with the right properties to be dark matter, but when you calculate how many of these particles would have been produced in the Big Bang and how many would have survived to the present day, you get the right number. The observed dark matter abundance falls out naturally from the calculation without any fine-tuning. This is the kind of coincidence that physicists call beautiful. It suggests you are on the right track. The other reason WIMPs were attractive is that they were detectable, in principle. A WIMP interacts through the weak force. This means that very occasionally, very rarely, but not impossibly rarely, a WIMP passing through a detector might collide with an atomic nucleus and transfer a tiny amount of energy to it. The nucleus would recoil slightly, emitting a detectable signal. With a large enough detector, sensitive enough instruments, and enough patience, you might catch one. This reasoning led to the construction of a series of increasingly large and increasingly sensitive underground detectors. Underground because you need to shield the detector from cosmic rays and other background radiation that would mimic the signal you are looking for. Cosmic rays shower down on Earth's surface constantly, and most particles they produce would trigger any particle detector continuously. By going deep underground, in mines, in mountain tunnels, under the Antarctic ice, you can block most of this background, leaving only the very occasional neutrino, and, if WIMPs exist, the very occasional WIMP. The first generation of WIMP detectors was built in the 1980s and 1990s. They were relatively small, kilograms of detector material, and relatively insensitive by modern standards. They found nothing. The second generation was larger. The cryogenic dark matter search, CDMS, operated in a former iron mine in northern Minnesota. It used germanium and silicon crystals cooled to within a fraction of a degree of absolute zero, sensitive to the tiny vibrations a WIMP collision would produce. It found no confirmed dark matter signals. The third generation was larger still. The LUX experiment, Large Underground Xenon, filled a tank with 370 kilograms of liquid xenon deep in a mine in South Dakota. It ran for years, looking for the faint flashes of light that would indicate a WIMP had struck a xenon nucleus. It found no confirmed dark matter signals. LUX was replaced by LZ, Lux Zeppelin, which uses 10 tons of liquid xenon, the most sensitive WIMP detector ever built. It is running now in the same mine in South Dakota, listening for collisions that have never come. So far, nothing. In parallel, the Large Hadron Collider at CERN began its first run in 2008, with one of its primary goals being the production of supersymmetric particles. If WIMPs exist with masses accessible to the LHC's energies, smashing protons together at near-light speeds should occasionally produce them. The detector signatures would include missing energy and missing momentum. The WIMP would escape the detector without leaving a trace, but its presence would be inferred from what is missing in the collision's energy budget. One of the LHC found the Higgs boson, the last missing particle of the Standard Model, in 2012. It found no supersymmetric particles. Run 2, at higher energies, found no supersymmetric particles. The LHC is currently in its third run, the most powerful yet. It has found nothing beyond the Standard Model. The absence of WIMPs is not yet proof that they do not exist. Detectors may not yet be sensitive enough. The LHC may not be operating at high enough energies. WIMPs may have properties that make them harder to detect than the simplest models predict. All of these are possible, but the most natural WIMP candidates, the ones predicted by the simplest versions of supersymmetry, have been ruled out. The parameter space in WIMPs can live, consistent with all the non-detections, is shrinking. Each year that passes without a detection is another year of data that constrains what WIMPs can be, if they exist at all. Many physicists who spent their careers searching for WIMPs are beginning to ask a different question. What if the WIMP is not the answer? If not WIMPs, then what? The list of dark matter candidates is long, and each one represents a different way of looking at the same mystery. The hunt has become more creative, more diverse, and in some ways more desperate as the WIMP paradigm has failed to deliver. The axion is perhaps the most theoretically well-motivated alternative. It was not invented to explain dark matter. It was invented to explain something else entirely, a deep theoretical puzzle called the strong CP problem. The strong nuclear force, which binds quarks together inside protons and neutrons and holds nuclei together, is described by a theory called quantum chromodynamics, or QCD. The equations of QCD have a term, a parameter called theta, that, based on the mathematics, could take any value from 0 to 2 pi. If theta has a large value, the strong force violates a symmetry called CP symmetry, meaning it would behave differently for matter and antimatter. This would produce observable effects. In particular, neutrons would have an electric dipole moment, a separation of positive and negative charge along their length. That would be measurable. Experiments have measured the neutron's electric dipole moment very precisely. It is essentially zero. This means theta must be extraordinarily close to zero, less than 10 to the minus 10. Even though there is no known reason it should not have a large value. Why should a free parameter in the theory of the strong force happen to be tuned to an absurdly small value? In 1977, physicists Roberto Peccei and Helen Quinn proposed an elegant solution. They introduced a new symmetry to the standard model that forces theta to zero dynamically. The symmetry was then spontaneously broken, producing a new particle, the axion, named by Frank Wilczek after a detergent brand because it cleaned up the strong CP problem. Wilczek received the Nobel Prize in Physics in 2004, partly for this work. Axions have properties that make them plausible dark matter candidates. They are very light, perhaps 1 trillion times lighter than the electron, which means they are not weakly interacting massive particles, but weakly interacting light particles, sometimes called WIMPs, opposite number. They interact very weakly with normal matter and light, and cosmological calculations suggest they could have been produced in the right abundance in the early universe to account for dark matter. Unlike WIMPs, which are individual heavy particles, axions, if they are dark matter, behave more like a field than like individual particles. The number of them is enormous. In every cubic centimeter of your body right now, there would be trillions of axions if they make up dark matter. They would be oscillating collectively as a coherent quantum wave. And occasionally, in a strong magnetic field, an axion can convert into a photon. This is the detection principle. The ADMX experiment, Axion Dark Matter Experiment, sits in a magnetic field of about 8 Tesla and looks for photons produced by axion-photon conversion. It is an extraordinarily sensitive microwave detector, listening for a signal that, if axions are dark matter, should be there. It has been running for years. So far, it has placed very tight limits on axion properties in certain mass ranges, but has found no confirmed dark matter signal. Other experiments, ABRACAD, ABRA, CASPER, Haystack, are searching complementary mass ranges. The technology is advancing rapidly, but no axion has been detected. Beyond WIMPs and axions, there are other candidates. Sterile neutrinos are hypothetical cousins of the 3 known neutrino flavors: electron neutrino, muon neutrino, tau neutrino, that interact even more weakly than the known neutrinos, so weakly that they have never been produced in any experiment. They are called sterile because they do not participate in the weak interaction at all, only in gravity. Some models suggest they could account for dark matter, and they might occasionally decay into a photon and a normal neutrino, producing a faint X-ray signal. A possible hint of such a signal was reported in 2014, a spectral line at 3.5 kilo-electron volts seen in multiple galaxy clusters and the Andromeda galaxy. The excitement was significant. Subsequent analysis has produced contradictory results, and the signal remains unconfirmed and contested. Primordial black holes are another possibility. These would be black holes that formed in the early universe, not from collapsing stars, but from density fluctuations during inflation. They would be black holes ranging from microscopic to many solar masses, formed billions of years before the first stars. They would have mass. They would interact only through gravity. They would be invisible. The detection of gravitational waves from black hole mergers by LIGO in 2015 briefly revived interest in primordial black holes as dark matter candidates, because some of the merging black holes had masses in a range unexpected for stellar origin black holes. But detailed analysis of gravitational lensing surveys has placed strong constraints on the abundance of primordial black holes in most mass ranges. They cannot be all of the dark matter. They might be some of it. And then there is ultralight dark matter, sometimes called fuzzy dark matter. Hypothetical particles so light that their quantum wavelength is enormous, comparable to the distance between galaxies. In this scenario, dark matter is not a collection of individual particles at all, but a quantum field that fills the universe with wave-like behavior on galactic scales. This model can explain certain puzzles about the internal structure of dark matter halos, puzzles that the standard WIMP model struggles with. But it raises its own theoretical questions. The diversity of candidates is not a sign of progress. It is a sign of how little we know. Each candidate requires a different detection strategy. Each strategy takes years to build, calibrate, and operate, and each has so far returned empty-handed. The history of dark matter detection experiments is one of the most sustained, expensive, and technically demanding scientific enterprises in history. It is also, so far, a history of failure. Not failure in the sense of bad science or wasted effort. The experiments have produced extraordinary advances in detector technology and have placed real, meaningful constraints on what dark matter can be. But failure in the sense that, after decades of increasingly sensitive searches, the thing being searched for has not been found. The first direct detection experiments operated in the 1980s. Physicists had calculated that if WIMPs make up the dark matter, and if WIMPs have masses of tens to hundreds of times the proton mass, then a kilogram of germanium or silicon or sodium iodide should register a handful of WIMP collisions per day. Not many, but enough to detect if your detector is sensitive enough and your backgrounds are low enough. The first experiments were far too small and far too noisy. Cosmic rays, radioactive contaminants in the detector materials and surrounding rock, vibrations from mine machinery, all of these produced signals that overwhelmed any potential dark matter signal. The first generation of experiments were largely exercises in learning how to make detectors quiet enough. They found nothing, but they established that the problem was harder than the first calculations suggested. Through the 1990s and 2000s, experiments got larger, deeper, and quieter. Detector materials were purified to extraordinary degrees. The germanium crystals used in CDMS were among the most chemically pure solid objects ever made. Experiments moved to mines thousands of meters underground, where the rock above provided the equivalent of 2 kilometers of water, shielding against cosmic rays. Electronic shielding, lead shielding, water shielding layers were added. Signal processing algorithms became more sophisticated. An episode that illustrates both the precision and the frustration of this field occurred with the Dama experiment in the Gran Sasso laboratory under the Apennine Mountains in Italy. Dama, dark matter experiment, uses sodium iodide crystals and has been running continuously since 1995. In 1998, the Dama collaboration reported a signal. The rate of scintillation events in their crystals varied with an annual modulation. It was higher in June and lower in December. This annual modulation is exactly what you would expect from dark matter. The Earth moves around the Sun, and the Sun moves through the galaxy. In June, the Earth's orbital velocity adds to the Sun's velocity through the dark matter halo. In December, the Earth's velocity subtracts from it. A detector moving faster through the dark matter wind sees more dark matter particles than one moving slower. An annual modulation in the event rate, peaking around June 2, is a predicted signature of dark matter interaction. Dama reported finding exactly this modulation, with a significance of many sigma, far beyond the 5 sigma threshold for a discovery claim. The signal has persisted for over 25 years of continuous operation. No systematic effect that could explain it has been identified, and yet no other experiment in the world has confirmed it. Every other experiment with comparable or greater sensitivity has looked in the parameter space where Dama's signal should appear, and found nothing. XEN, ON1T, Lux, Panda X, CDMS, all of them have excluded the dark matter interpretations of Dama's signal with high confidence. The contradiction has never been resolved. Most physicists believe Dama is seeing some systematic effect they have not identified. Some believe Dama is seeing something real that the other experiments cannot see because of their different detector materials. The debate continues, unresolved, after a quarter century. The LHC presents a different kind of frustration. The machine was designed in part to find physics beyond the standard model. Supersymmetry was the leading candidate. Run 1 found the Higgs boson in 2012, completing the standard model, and found nothing else. This was celebrated as a triumph for the standard model and a puzzle for beyond standard model physics. The neutralino, the most natural WIMP candidate, was expected to appear in the LHC's collisions if it had a mass accessible to the machine's energies. It did not. Run 2 extended the search to higher masses and more sensitive analyses. Nothing. The parameter space where the simplest supersymmetric theories predicted dark matter has been largely ruled out. Indirect detection represents a third approach. If dark matter particles exist in the galaxy, and if they occasionally annihilate with each other, particle meeting antiparticle, producing a burst of ordinary particles, then those ordinary particles should be detectable. The center of the Milky Way, where dark matter is densest, should glow faintly in gamma rays from such annihilations. Space-based gamma-ray telescopes like Fermi-LAT have searched for this signal. There are hints, an excess of gamma rays from the galactic center that matches what dark matter annihilation might produce. But the signal can also be explained by ordinary pulsars, and the debate is ongoing. The story of dark matter detection is a story of extraordinary technical achievement producing extraordinary null results. The experiments are real. The constraints are real. The dark matter is real. The identity of the dark matter remains, after all of this, completely unknown. To fully appreciate what dark matter has done, you need to see the universe on its largest scales, not the scale of a galaxy or a galaxy cluster. The scale at which the entire observable universe becomes a single object of study. The cosmic web is the large-scale structure of the universe. It is the pattern of how matter, dark and visible, is distributed across billions of light years. And it is one of the most striking objects in the universe, visible only in data, assembled by astronomers mapping the positions and distances of millions of galaxies. The cosmic web looks like a web, like the silk threads of an enormous spider's work, or the foam on a beer left sitting for too long, or the network of neurons in a brain. It has 3 components: filaments, nodes, and voids. Filaments are long, thread-like structures of matter, dark matter with normal matter following along, stretching for hundreds of millions of light years. They are not solid structures. They are more like rivers of matter, flows along which galaxies are strung like beads on a wire. Nodes are where the filaments intersect, the densest regions of the universe. Galaxy clusters, collections of hundreds or thousands of galaxies swimming in vast halos of hot gas, themselves embedded in massive dark matter concentrations. The Coma cluster that Zwicky studied, the Virgo cluster at the center of our local supercluster, the Perseus cluster, one of the brightest X-ray sources in the sky. These are the nodes of the cosmic web, and voids are the spaces between the filaments, vast, nearly empty regions where very little exists. The Boötis void, discovered in 1981, is roughly 330 million light-years across and contains barely 60 galaxies where 10,000 would be expected. An observer in the center of the Boötis void would look out in every direction and see essentially nothing. The nearest galaxy cluster hundreds of millions of light-years away. The night sky would be almost completely dark. The cosmic web emerged from the initial density fluctuations left by inflation, amplified over 13 billion years by gravity. Dark matter, collapsing first, formed the scaffolding of the web. Normal matter followed. The voids emptied as matter drained toward the filaments. The filaments fed the nodes. The nodes grew into the great clusters we observe today. Computer simulations of cosmic structure formation, most famously, the Millennium simulation run by the Virgo Consortium in 2005, using some of the most powerful computers available at the time, reproduce the cosmic web with extraordinary fidelity when dark matter is included. The simulated universe looks, on large scales, essentially identical to the observed universe. The statistics of voids, filaments, and clusters in the simulation match the statistics of voids, filaments, and clusters in the real universe. Without dark matter, in simulations run with only normal matter and no dark matter, the structure is wrong. Galaxies do not form at the right time. They do not cluster in the right way. The cosmic web does not emerge. The universe looks nothing like what we observe. This is perhaps the most compelling argument for dark matter of all. Not the rotation curves of individual galaxies, not the dynamics of the bullet cluster, but the entire large-scale structure of the observable universe. The distribution of every galaxy in the observable universe, mapped across billions of light-years, can be reproduced by simulation only when dark matter is included. It cannot be reproduced without it. No modification of gravity that has been proposed can account for this. The cosmic web is dark matter's signature, written across the largest scales in the universe, legible only if you know how to read it. The Sloan Digital Sky Survey, the largest three-dimensional map of the universe ever constructed, has mapped the positions of more than 3 million galaxies and quasars across a quarter of the sky. The cosmic web is unmistakable in the data. The filaments, the voids, the nodes, all exactly where dark matter simulations predicted they would be. The DESI survey currently underway is mapping over 40 million galaxies and will produce the most detailed picture yet of the cosmic web structure. Every galaxy in those surveys lives in a dark matter halo. Every filament connecting galaxy clusters is a dark matter filament. Every void that separates them is emptied by dark matter dynamics. The visible universe is a decoration on a dark matter armature that we cannot see but can read in every structure the visible universe contains. In 2018, a paper was published in the journal Nature that caused something close to panic in the dark matter community. Not because it challenged the existence of dark matter. It did not. But because it reported something that the standard theory of galaxy formation said should not exist. A galaxy with almost no dark matter. The galaxy is called NGC 1052, DF2. It is a faint, low-surface brightness galaxy about 65 million light-years away, discovered by astronomer Peter van Dokkum and his colleagues using the Dragonfly telephoto array, an unusual instrument built from an array of camera lenses that excels at detecting faint diffuse light. NGC 1052. DF2 is a large galaxy by diameter, about 20,000 light-years across, but contains very few stars for its size, just a few 100 million solar masses of stellar material. Van Dokkum and his team measured the velocities of the galaxy's globular clusters, old, dense balls of stars that orbit the galaxy like satellites, and used those velocities to infer the galaxy's total mass. What they found was that the total mass was essentially equal to the mass of the visible stars. There was no evidence of a dark matter halo. Or if there was a halo, it was at most a small fraction of what you would expect for a galaxy of that size. This was extraordinary. Every galaxy ever studied before, from the largest ellipticals to the smallest dwarf galaxies, had been found to contain far more dark matter than normal matter. The ratio could vary, but dark matter always dominated. A galaxy with essentially no dark matter had never been found. The result was controversial. Some astronomers questioned the distance estimate. If the galaxy were closer than Van Dokkum claimed, the velocity measurements would imply more dark matter. The debate has continued for years, with multiple independent teams weighing in on the distance. The current consensus places the galaxy at the distance originally claimed, confirming that it is genuinely dark matter deficient. Shortly after, Van Dokkum's team found another such galaxy in the same vicinity, NGC 1052, DF4, that is also almost completely dark matter-free. And then more. There appear to be a population of these objects, ultra-diffuse galaxies, with very little dark matter, concentrated in the vicinity of the giant elliptical galaxy NGC 1052. What does this mean? The leading explanation is that these galaxies lost their dark matter through tidal stripping. NGC 1052 is a large, massive galaxy with enormous gravitational influence. If the ultra-diffuse galaxies formed near it, or passed close to it, tidal forces from NGC 1052 could have stripped away their dark matter halos while leaving the more tightly bound stellar material relatively intact. The dark matter, being more extended and loosely bound, would be stripped first. This explanation is consistent with the dark matter model. It actually provides a kind of confirmation. If dark matter is a real, physical component that can be gravitationally stripped away from a galaxy, then finding galaxies that have lost their dark matter through this process is not evidence against dark matter. It is evidence for it. It shows that dark matter can be separated from normal matter by gravitational interactions, which is exactly what the bullet cluster showed. But the existence of these dark matter-deficient galaxies raises its own puzzles. How did they form stars in the first place? Without a dark matter halo to provide the gravitational well, how did gas collapse into stars? They might have formed inside a dark matter halo that was subsequently stripped. They might have formed in an unusual way. The details are not fully understood. What the dark matter-deficient galaxies illustrate, more than anything, is how central dark matter is to everything we think we understand about galaxy formation. A galaxy without dark matter is so anomalous that its discovery caused years of controversy and has still not been fully explained. Dark matter is not a peripheral feature of galaxy physics. It is the primary ingredient. The most independent and, in some ways, most compelling evidence for dark matter comes from the oldest light in the universe, the cosmic microwave background radiation. The CMB is a faint glow of microwave radiation that fills the entire sky, a relic from the moment, 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with protons, and the universe became transparent to light. Before that moment, the universe was an opaque plasma. Photons were constantly scattered by free electrons, unable to travel more than a short distance before being deflected. After that moment, called recombination, photons streamed freely across the universe for the first time. The photons we detect today as the CMB have been traveling since that moment, 13.4 billion years ago, redshifted from visible light to microwaves by the expansion of the universe. The CMB is almost perfectly uniform, a blackbody spectrum at 2.725 Kelvin, but not quite. Tiny temperature fluctuations of roughly 1 part in 100,000 are present across the sky. These fluctuations are the imprint of the density variations in the early universe, the seeds of all cosmic structure, and their pattern contains, encoded within it, detailed information about the composition of the universe. The temperature fluctuations in the CMB are not random. They have a specific statistical structure, a power spectrum, describing how much variation exists at different angular scales. This power spectrum has peaks and troughs, called acoustic peaks, reflecting the acoustic oscillations, the sound waves, that were ringing through the early universe before recombination. The positions, heights, and widths of these acoustic peaks depend sensitively on the composition of the universe. How much normal matter? How much dark matter? How much dark energy? The presence of dark matter leaves a specific signature in the acoustic peaks that normal matter alone cannot produce. The reason is subtle, but important. Normal matter and dark matter respond differently to gravity in the early universe because normal matter is coupled to photons and dark matter is not. In the acoustic oscillations, normal matter is driven by both gravity and radiation pressure, while dark matter is driven only by gravity. The ratio of dark matter to normal matter determines the relative amplitudes of the odd and even acoustic peaks in the power spectrum. Measurements of the CMB, first by the COBE satellite in 1992, then more precisely by WMAP from 2001 to 2010, and most precisely of all, by the Planck satellite from 2009 to 2013, have measured the acoustic peak structure of the CMB with extraordinary precision. The result is unambiguous. The CMB power spectrum is consistent with a universe containing approximately 5% normal matter, 27% dark matter, and 68% dark energy. It is inconsistent with any model that lacks dark matter. This measurement is entirely independent of galaxy rotation curves, galaxy cluster dynamics, gravitational lensing, and large-scale structure. It uses different physics, different observations, different analysis methods, and it arrives at the same answer. This convergence from completely independent observational lines, using completely different physics all pointing to 27% dark matter, is why the scientific community is so confident that dark matter exists. It is not based on a single measurement that might be wrong. It is based on a dozen independent measurements, using completely different instruments and techniques, all pointing to the same number. What the CMB cannot tell us is what dark matter is. It tells us how much there is. It tells us its gravitational behavior. It cannot tell us its particle identity, its mass, its interactions beyond gravity. For that, we need direct detection. And that is where the silence continues. After 40 years of direct detection experiments, 2 decades of LHC operation, decades of indirect searches from space, and millions of scientific person-hours, the total number of confirmed dark matter detections stands at 0. This is not what anyone expected. And the failure to find dark matter is beginning to reshape how physicists think about the problem. The most natural WIMP candidates, the ones that the simplest supersymmetric theories predicted, the ones with masses accessible to the LHC and interaction strengths accessible to first-generation direct detection experiments, have been ruled out. Not all WIMPs have been ruled out. Not even close. The parameter space of possible WIMP masses and interaction strengths is vast, and experiments have only eliminated a portion of it. But the most theoretically motivated portion, the part that physicists were most excited about 40 years ago, has been searched and found empty. This has produced a crisis of confidence in the WIMP paradigm. Not a scientific crisis. The evidence for dark matter itself is as strong as ever. But a theoretical crisis. What if our intuitions about what dark matter should be were simply wrong? The WIMP miracle, the fact that the simplest supersymmetric particles would naturally have the right abundance, was compelling, but it may have been a misleading coincidence. The history of physics is full of cases where a beautiful theoretical prediction turned out not to describe nature. Sometimes nature prefers the inelegant solution. Some physicists are now arguing for a broader search strategy. The WIMP has dominated dark matter research for 40 years because it was theoretically well motivated and experimentally accessible. But dark matter does not have to be a WIMP. It could be any of a vast range of particles with a vast range of masses and a vast range of interaction strengths. Some of these candidates: ultralight particles, super heavy particles, particles that interact even more weakly than WIMPs, require completely different detection strategies that are only now being developed. The absence of WIMPs has also led to a revival of interest in alternative gravity theories. While the bullet cluster makes it very difficult for any simple modification of gravity to explain dark matter, there are more sophisticated frameworks, such as tensor vector scalar gravity and certain relativistic generalizations of Mond, that can account for some of the evidence. None has yet been able to explain all of it. But the failure to detect the particle has sent some physicists back to the gravitational drawing board. There is also the possibility that dark matter interacts with itself, not just with normal matter and gravity. Self-interacting dark matter, SIDM, is a model in which dark matter particles occasionally scatter off each other. This does not help with direct detection, since the experiments are looking for interactions with normal matter. But SIDM makes different predictions about the internal structure of dark matter halos. And there are some observational hints from the structure of small galaxies and galaxy clusters that might favor self-interacting dark matter over the standard, non-interacting variety. The evidence is not conclusive. The most unsettling possibility is one that physicists rarely state explicitly, but increasingly whisper: dark matter might be genuinely undetectable. At least with any technology foreseeable in the next several decades. If dark matter interacts with normal matter only through gravity, if it has no weak force interaction, no electromagnetic interaction, nothing, then there is no direct detection signal possible. The only way to detect it would be through its gravitational effects on normal matter, which is exactly what astronomers have been doing for a century. The particle itself would be permanently hidden. This would be a strange situation for physics. We would know that something exists. We would know roughly how much of it there is. We would know what it does. And we would have no way of ever knowing what it is. A substance that makes up a quarter of the universe, detectable only by its gravitational shadow, its particle identity permanently beyond reach. This is not an outcome physics has ever faced before. It would require a rethinking of what it means to explain something. Normally, knowing something exists and knowing what it does is considered the beginning of understanding. The next step is to understand what it is, how it is constituted, what its internal properties are. If dark matter is detectable only gravitationally, that next step may never be possible. The mystery may be permanent. As of today, the dark matter search is more active than it has ever been. Experiments that would have seemed impossibly ambitious 20 years ago are now running or under construction. The field has adapted to the failure of the WIMP paradigm by broadening its scope, developing new technologies, and searching in new directions. The LZ experiment, Lux Zeppelin, is currently the world's most sensitive WIMP detector. It holds 10 tons of liquid xenon in a tank deep in the Sanford Underground Research Facility in Lead, South Dakota, at a depth equivalent to nearly 2 kilometers of water. The xenon is purified to reduce radioactive contamination to vanishingly small levels. The detector is surrounded by layers of shielding: a water tank, a lead shield, a polyethylene shield, to reduce background from external radiation. It is operating now, accumulating data, looking for the faint flicker of a WIMP collision against a xenon nucleus. Its sensitivity is extraordinary. LZ can detect interactions so rare that a WIMP would have to pass through an amount of xenon equivalent to thousands of Earths to produce even one collision. If WIMPs exist and have the properties that many models predict, LZ should see them. If it does not see them in its projected running time, it will push the WIMP parameter space into regions where even the most optimistic theoretical models struggle to survive. The ADMX experiment is searching for axions in the microwave frequency range, tuning a sensitive cavity resonator through different frequencies, listening for the conversion of axion dark matter into photons. It has achieved sensitivity levels that probe genuinely interesting axion models. The DMR radio experiment, under development at Stanford, will extend the axion search to much lower frequencies. XLZD, the planned successor to LZ, would be an order of magnitude larger still, perhaps 100 tons of xenon. Such a detector would face a new and irreducible background: neutrinos from the Sun and from supernova remnants, which produce nuclear recoils indistinguishable from WIMP collisions. This is called the neutrino flaw, or more recently the neutrino fog, and it represents a fundamental limit to the sensitivity of traditional WIMP searches. Getting below the neutrino fog would require directional detectors, instruments that can measure not just the recoil energy, but the direction of the recoil, allowing WIMP collisions to be distinguished from neutrino interactions because they come from the direction of the galactic center rather than from the Sun. No such directional detector at useful scale yet exists. The Vera Rubin Observatory, named for the astronomer who proved dark matter's existence, is a new telescope being commissioned in Chile that will conduct the legacy survey of space and time. A 10-year program to photograph the entire southern sky repeatedly, building a map of gravitational lensing across billions of galaxies. This will provide the most detailed picture yet of the dark matter distribution across the universe, revealing the structure of dark matter halos, the patterns of the cosmic web, the growth of structure over cosmic time. It will not directly detect dark matter particles, but it will constrain dark matter's properties more tightly than ever before. The Euclid Space Telescope, launched in 2023, is surveying the geometry of the universe using weak gravitational lensing and galaxy clustering, building a three-dimensional map of dark matter distribution across 10 billion years of cosmic history. Its data will test whether dark matter behaves as the Standard Model predicts, or whether there are hints of new physics. And the Square Kilometre Array, SKA, a vast radio telescope being constructed across South Africa and Australia, will observe hydrogen gas in galaxies across cosmic time, providing independent measurements of galaxy rotation curves and dark matter halos on scales never before accessible. The search has never been better resourced. The technology has never been more sophisticated. The theoretical framework has never been more carefully developed. And the mystery remains exactly as deep as it was when Fritz Zwicky first noticed something wrong in 1933. We are looking harder than ever, and we have still found nothing. Right now, as you lie here, dark matter is passing through you. This is not a metaphor. It is not a philosophical statement. It is straightforward physics. If dark matter is a particle, which most physicists believe, then the Milky Way's dark matter halo is filled with these particles, distributed throughout the volume of the galaxy and extending far beyond its visible disk. The Earth, orbiting the Sun at 220 kilometers per second around the galactic center, is moving through this halo. Dark matter particles are streaming through the Earth at that velocity from all directions. The numbers are staggering. In each cubic centimeter of space near Earth, there are approximately 0.3 GeV of dark matter energy density, roughly the energy equivalent of a proton's mass per cubic centimeter. If dark matter consists of WIMP-like particles with a mass of around 100 GeV, one of the most commonly assumed masses, then there are about 1 million dark matter particles in every cubic meter of space around you right now. 1 billion pass through your body every second, through your hands, your head, your heart, through the bed you are lying on, through the floor, through the earth below. They do not slow down. They do not interact with the atoms in your body in any way you can feel. No heat is deposited. No cells are damaged. No signal reaches your nervous system. The particles pass through as if you were not there, because to them, in the sense that matters physically, you are not there. You are made of normal matter, which they ignore completely. The only reason we know they are passing through is that we can infer their presence from the gravitational effects they have on galactic scales. On the scale of a human being, on the scale of an entire planet, dark matter's gravitational effect is completely negligible. It is there. It has mass. But the mass of dark matter in a volume the size of the Earth is tiny compared to the mass of the Earth itself, and gravity is the weakest of the forces. You could not feel it, even if you tried. This is the profound strangeness of the situation. The substance that makes up 27% of the universe, the substance that built every galaxy that exists, that shaped the cosmic web across billions of light years, that is fundamental to every structure in the cosmos, is, from your personal perspective, completely absent, invisible, imperceptible, as if it does not exist. You live inside a dark matter halo that extends 600,000 light-years in every direction. The visible galaxy you see in the night sky, the band of the Milky Way stretching across the sky, is a thin disk of stars and gas at the center of this vast invisible sphere. The sphere is 10 times more massive than the disk. It is older than the disk. It formed before the disk. In a very real sense, it is more the galaxy than the disk is. But you will never see it. You cannot. No wavelength of light will reveal it. No telescope, however large, however sensitive, can photograph it. The instrument that would allow you to see the dark matter halo of the Milky Way does not exist and may never exist. You are inside something enormous and invisible, and you are made of the thin residue of normal matter that settled into its core. The universe is mostly something else, and you are made of the something that isn't that. There is something both humbling and remarkable about this. The atoms that make up your body, the carbon, the oxygen, the iron, are the rare kind of matter, the ordinary kind, the visible kind, the kind that interacts with light and makes chemistry possible and makes biology possible and makes consciousness possible. And this ordinary matter, this 5% residue of the universe's mass, is the only kind of matter that can sit in a dark room and wonder about the other 27%. Dark matter cannot think. It cannot feel. Whatever it is made of, it does not do chemistry. It does not form molecules. It does not cluster into complex structures on human scales. It passes through everything, feels nothing beyond gravity, leaves no mark. The universe gave dark matter mass and mystery. It gave normal matter the ability to wonder. There is a technique that allows astronomers to map dark matter without ever detecting a single dark matter particle. It does not require any assumption about what dark matter is made of. It does not require dark matter to interact with any detector. It requires only that dark matter has mass, and that mass curves space-time. And that is the one thing about dark matter we know for certain. The technique is gravitational lensing. Einstein's general theory of relativity predicts that mass warps the geometry of space around it. Light, following the straightest possible path through curved space, is deflected by massive objects. The larger the mass, the stronger the deflection. This was confirmed in 1919 when Arthur Eddington measured the deflection of starlight passing near the sun during a solar eclipse, finding that the stars near the sun's limb appeared to be shifted from their true positions by almost exactly the amount Einstein's equations predicted. The result made Einstein famous overnight. Gravitational lensing by galaxies and galaxy clusters is far more dramatic than lensing by a single star. A galaxy cluster with a mass of 1,000 trillion suns deflects background light so strongly that it produces spectacular visible effects. Distant galaxies, seen through a massive cluster, appear distorted, stretched into arcs, sometimes split into multiple images, occasionally bent into complete rings of light, called Einstein rings, when the geometry is exactly right. These arcs and rings and distorted images are not an illusion. They are the actual light from distant galaxies, bent and redirected by the gravity of the intervening cluster. By measuring how distorted the background galaxies appear, and knowing the geometry of the situation, the distances to the lens, and the source, astronomers can calculate the total mass of the lensing object. Not just the mass of the visible gas and stars, the total mass, including any invisible component. And the total mass is always much larger than the visible mass. This is called strong gravitational lensing, and it applies in the regions closest to the most massive concentrations of matter. But there is also weak gravitational lensing, which applies across much larger areas. In the outskirts of galaxy clusters and in the filaments of the cosmic web, the lensing is too weak to produce arcs or multiple images. But it produces a subtle, coherent distortion of background galaxy shapes. Galaxies that are physically round appear slightly elongated, preferentially stretched in the direction perpendicular to the line toward the nearest mass concentration. This stretching is tiny, a few percent, and invisible in any individual galaxy. Because galaxies are not intrinsically round, they have random orientations and shapes. But statistically, across thousands or millions of background galaxies, the coherent alignment produced by gravitational lensing can be detected. Regions of higher mass produce more lensing and more distortion. By measuring the statistical alignment of millions of background galaxies, astronomers can reconstruct a map of the dark matter distribution across enormous volumes of space. The most comprehensive weak lensing surveys have mapped the dark matter distribution across a quarter of the sky, finding the cosmic web structure, filaments, voids, nodes, in dark matter precisely where the models predict. The Kilo-Degree Survey, the Dark Energy Survey, and the Hyper-Suprime Cam Survey have all produced such maps. They agree with each other and with the predictions of the standard dark matter model to a remarkable degree. What gravitational lensing gives us that no other technique provides is a direct, assumption-free measurement of where the mass is. Galaxy rotation curves tell you about the mass distribution within a galaxy. X-ray observations tell you about the hot gas in a cluster. But gravitational lensing tells you about all the mass, everywhere, without any assumption about what the mass is made of or how it behaves. And what it tells us is consistent. There is approximately 5 to 6 times as much invisible mass as visible mass in every region of the universe. The invisible mass forms halos around galaxies, concentrations in galaxy clusters, and a web of filaments connecting the densest regions. One of the most beautiful demonstrations of gravitational lensing's power is the Hubble Frontier Fields program, in which the Hubble Space Telescope spent extraordinary amounts of observing time on 6 massive galaxy clusters, using them as cosmic telescopes to magnify extremely distant galaxies behind them. In the process, the program produced detailed dark matter maps of each cluster, revealing the complex, lumpy, asymmetric structure of the dark matter distribution. Structure that matches what theoretical simulations predict for the merger histories of galaxy clusters that have been pulled together from multiple smaller concentrations over billions of years. The JWST, the James Webb Space Telescope, is now being used for similar programs with far greater depth and resolution. It is showing dark matter structures in clusters at unprecedented detail, revealing fine structure in the dark matter distribution that serves as a precision test of theoretical models. Every observation is consistent with dark matter being real. None has yet revealed what it is. This is the fundamental situation. We can see dark matter in the sense that we can see its gravitational effects on light. We can photograph its effects. We can map its distribution. We can weigh it. We can watch it shape the universe. What we cannot do is touch it, detect it directly, or identify its particle nature. We have extraordinarily detailed photographs of the shadow, without any knowledge of the object casting the shadow. To understand why dark matter has the properties it has, why it is cold rather than hot, why it is slow-moving rather than relativistic, why it forms the specific structures we observe, you need to understand where it came from. You need to go back to the first second of the universe's existence. In the first fraction of a second after the Big Bang, the universe was a thermal bath of all particles. The temperature was so high that particles could be created from energy and annihilated back into energy in continuous equilibrium. Quarks and antiquarks, electrons and positrons, photons, neutrinos, and, if they exist, dark matter particles. all of them in constant creation and annihilation, in thermal equilibrium with each other. As the universe expanded, it cooled, and as it cooled, a process called freeze-out occurred. For each type of particle, there is a temperature below which the thermal bath no longer has enough energy to create new pairs of that particle from collisions. At that point, creation stops. Annihilation continues for a while, as existing particles find their antiparticles and annihilate. But eventually, as the universe expands and the density drops, the remaining particles are too sparse to find each other and annihilate. They decouple from the thermal bath. They freeze out. Their number is fixed. This freeze-out process determines how many particles of each type survive to the present day. The key parameter is the interaction strength, how efficiently a particle interacts with the thermal bath. Particles that interact more strongly freeze out later, when the universe is cooler and denser, and their surviving number is lower. Particles that interact very weakly freeze out earlier, when the universe is hotter and less dense, and their surviving number is higher. For dark matter particles with the interaction strength of the weak nuclear force, WIMPs, the freeze-out calculation gives a surviving abundance that matches the observed dark matter density today. This is the WIMP miracle. The interaction strength required for the weak nuclear force naturally produces the right dark matter abundance without any fine-tuning. But there is a subtlety. The calculation works for dark matter that is cold, moving much slower than light at the time of structure formation. Hot dark matter, moving at relativistic speeds, would free stream out of small-scale density fluctuations, washing them out. If dark matter were hot, the first structures to form would be the largest, superclusters, and smaller structures like galaxies would only form later by fragmentation. This is the top-down scenario. Observations rule this out. The cosmic web structure we observe is consistent with structure forming from the bottom up. Small halos forming first, then merging into larger ones. This is the cold dark matter scenario, where dark matter is non-relativistic, slow-moving, at the time of structure formation. Cold dark matter allows small-scale structure to form first, and this is what we see. Neutrinos are the one particle in the Standard Model that could contribute to dark matter. They are extremely light, weakly interacting, and produced in enormous numbers in the early universe. But neutrinos are hot dark matter. They move at relativistic speeds and free stream on the scales of galaxy clusters, washing out structure. The cosmic web structure rules out neutrinos as the dominant dark matter component, though neutrinos do contribute a small fraction. The dominant component must be cold. The most precise constraints on dark matter's properties come from the cosmic microwave background and the large-scale structure of the universe. Together, they require dark matter to be cold, non-interacting with itself, or nearly so in the simplest models, produced in the right abundance in the early universe, and stable, not decaying into other particles on timescales shorter than the age of the universe. These constraints are satisfied by a wide range of particle candidates. They do not identify which candidate is right. The early universe also sets limits on how light dark matter can be. If dark matter particles are very light, they can free stream and wash out small-scale structure. This is why there is a lower limit on the dark matter particle mass, typically somewhere around a few kilo-electron volts, though the exact number depends on the model. Particles lighter than this would be warm dark matter or hot dark matter, and observational constraints from the matter power spectrum and the Lyman alpha forest are tight. The Lyman Alpha Forest is a remarkable observational tool for constraining dark matter. When we observe the spectra of distant quasars, brilliant active galactic nuclei at the edge of the observable universe, we see a forest of absorption lines produced by hydrogen gas between us and the quasar. Each absorption line corresponds to a cloud of gas at a specific redshift, absorbing specific wavelengths of light. The pattern of these absorption lines traces the large-scale structure of matter, specifically the dark matter filaments that the hydrogen gas follows. The statistical properties of the Lyman Alpha Forest can be compared with predictions from dark matter models. Warm dark matter models, where the dark matter particle is lighter and moves faster, predicts smoother structure at small scales, erasing the fine structure visible in the Lyman Alpha Forest. Cold dark matter predicts more fine structure. The observations are consistent with cold dark matter and constrain warm dark matter models tightly. All of these constraints, the CMB, the large-scale structure, the Lyman Alpha Forest, the galaxy rotation curves, the cluster dynamics, consistently require dark matter to be cold, stable, non-baryonic, and gravitationally interacting. They do not yet tell us which particle it is, but they tell us, in remarkable detail, what kind of thing it must be. The particle that fits all these requirements is out there. It has been there since the first second of the universe. It built the galaxies. It is here now. We just cannot find it. The standard cold dark matter model, which assumes dark matter particles are non-relativistic, non-interacting, and produce the cosmic web structure through hierarchical clustering, is extraordinarily successful at explaining the universe on large scales, the distribution of galaxies across billions of light-years, the statistics of galaxy clusters, the acoustic peaks of the cosmic microwave background. All of these are predicted with remarkable accuracy by the standard model. But on small scales, on the scales of individual dwarf galaxies and the innermost regions of dark matter halos, there are puzzles. Observations do not quite match what the simplest cold dark matter models predict. These discrepancies are known collectively as the small-scale crisis in cold dark matter, and they have been a subject of intense debate for 2 decades. The first puzzle is called the missing satellites problem. The standard cold dark matter model predicts that large galaxies like the Milky Way should be surrounded by hundreds or even thousands of smaller dwarf satellite galaxies. The dark matter model produces an enormous number of small subhalos, dark matter concentrations below the mass threshold needed to form visible galaxies. But many of these should be massive enough to contain at least some stars. The actual number of known satellite galaxies around the Milky Way is much smaller. The Milky Way has about 60 confirmed satellite galaxies. Models predict something like 1,000. The discrepancy might not be as large as it appears. Many of the predicted small satellites might simply be too faint to have been detected yet. Sky surveys have become much more sensitive in recent years, and the number of known ultra-faint dwarf satellites has grown significantly as survey depth has increased. The Large Synoptic Survey Telescope, now called the Vera Rubin Observatory, is expected to discover many more. It is possible that the missing satellites are simply missing from the observations, not from the universe. But there are deeper problems. The too big to fail problem asks why the Milky Way's most massive satellite galaxies, the ones that should certainly contain stars, are less dense in their interiors than the standard model predicts. The dark matter halos predicted by the model for objects of this mass should be much denser at their centers, than the actual satellite galaxies appear to be. Why would the biggest, most massive satellites fail to live up to the predictions? The cusp core problem is related. Standard cold dark matter simulations predict that dark matter halos should have a density profile that rises steeply toward the center, a cusp. But observations of the inner regions of dwarf galaxies, which are dominated by dark matter, and therefore provide the cleanest test, often find a flat central density, a core, rather than the predicted cusp. The dark matter appears to be less concentrated in the centers of small galaxies than the model predicts. These discrepancies could have several explanations. The most straightforward is that baryonic processes, the effects of the normal matter gas and stars that are not included in pure dark matter simulations, can significantly modify the dark matter distribution. When massive stars explode as supernovae, they drive powerful outflows of gas from the galaxy's central region. These outflows remove mass from the center and change the gravitational potential, causing the dark matter to expand and flatten into a core, rather than remaining in a cusp. This process, called supernova-driven dark matter core formation, is now included in the most sophisticated galaxy formation simulations. When these baryonic effects are included, many of the small-scale discrepancies are reduced or eliminated. Simulations that include realistic models of star formation and supernova feedback can produce dwarf galaxies with cores rather than cusps, can explain the reduced number of luminous satellites, and can explain the too-big-to-fail problem. The question is whether the baryonic physics models are realistic enough. But some physicists argue that the small-scale problems are telling us something more fundamental. Self-interacting dark matter, SIDM, is a model in which dark matter particles occasionally scatter off each other, transferring momentum in a process analogous to ordinary gas pressure. If dark matter particles scatter off each other frequently enough, they can transfer energy from the dense inner regions of a halo to the outer regions, reducing the central density and creating a core rather than a cusp. The SIDM interaction rate required to explain the observations is small, much smaller than ordinary matter interactions, but non-negligible. Self-interacting dark matter makes specific predictions about how the central density of dark matter halos should scale with halo mass, and about how it should be affected by the environment. For example, galaxies in denser environments that experience more dark matter scattering, should have different core profiles than isolated galaxies. These predictions can be tested with current and future observations. Fuzzy dark matter, ultralight dark matter, takes a different approach. If dark matter particles have masses around 10 to the minus 20 2 electron volts, some 22 orders of magnitude lighter than the electron, then their quantum mechanical wavelength is comparable to the size of a dwarf galaxy. This means dark matter in these galaxies behaves more like a quantum fluid than like a collection of individual particles. The quantum pressure of this fluid resists compression below the characteristic quantum length scale, naturally producing cores rather than cusps. Fuzzy dark matter also suppresses the formation of structure below a certain scale, potentially explaining the reduced number of small satellites. None of these solutions has yet been definitively confirmed or ruled out. The small-scale crisis might be solved by baryonic physics, or by dark matter self-interactions, or by the quantum nature of ultralight dark matter, or by some combination of all three. The resolution of the small-scale problems is one of the most active areas of research in cosmology, and it is producing new constraints on dark matter properties that complement the direct detection searches. The frustrating truth is that every approach to studying dark matter, direct detection, indirect detection, particle accelerators, gravitational lensing, galaxy dynamics, the small-scale structure of dwarf galaxies, has produced real constraints, real insight, and zero confirmed identifications. The dark matter is real. Its effects are everywhere. Its identity is nowhere. It is worth asking a question that physics rarely asks, because it is uncomfortable. What happens if we never directly detect dark matter? What happens if the next generation of experiments comes back empty? And the generation after that? And the generation after that? At what point does the absence of detection start to tell us something new? The answer depends on what dark matter is. If dark matter is a WIMP, with the properties that the most motivated theoretical models predict, then the current experiments are on the verge of ruling it out, definitively. The LZ experiment and its successors will probe the remaining natural WIMP parameter space within the next decade or two. If they find nothing, the WIMP will be ruled out for all practical purposes. That would be an extraordinary result. Not a discovery, but a decisive elimination that would force the field to completely rethink its approach. If dark matter is an axion, the axion parameter space is much larger and the experiments much more technically challenging. Axion searches cover a vast range of possible masses, and the technology to search at most of that range has not yet been developed. The axion might hide for decades more, simply because we lack the instruments to detect it. Absence of detection in the current axion experiments does not yet constitute strong evidence against the axion. If dark matter interacts with normal matter only through gravity, then direct detection is permanently impossible. No experiment can detect pure gravitational interactions between dark matter and detector nuclei. The signal would be far below any conceivable detection threshold. In this case, we would be left with only indirect and astronomical constraints on dark matter's properties. We could measure its distribution, its large-scale behavior, its effect on galaxies and clusters, and the cosmic web. We could determine many of its properties, but we could never measure its mass, its quantum numbers, its particle identity. This would represent a fundamental limit on scientific knowledge of a specific and unusual kind. Not the familiar limit of experiments being too hard to perform, or theories being too difficult to test, but a deeper limit. A component of nature that makes up 27% of the universe and is accessible only through its gravitational shadow, permanently hidden from any more direct investigation. Physics has occasionally encountered such limits before. The interior of a black hole is in principle forever beyond observation from outside. The state of the universe before the Big Bang, or before the Planck time, is in principle inaccessible because our theories of space-time break down. These limits are accepted as fundamental features of the structure of knowledge. A gravitationally only interacting dark matter would be different in character, because the object is not hidden by a horizon or by the breakdown of theory. It is right here, flowing through us, gravitationally present, simply fundamentally non-interacting with the instruments we can build. The history of physics suggests this outcome is unlikely. Every time a new phenomenon has been discovered, electromagnetism, radioactivity, nuclear forces, the weak interaction, it has eventually been understood in terms of some fundamental interaction that was ultimately detectable. The universe has generally been kind to curious observers, providing phenomena that, with enough ingenuity, can be detected and characterized. But dark matter has been unusually uncooperative. 100 years of hints and indirect evidence and not a single confirmed detection. It is possible that nature is telling us something, that our intuitions about what dark matter should be, formed by analogy with particles we already know, are wrong. The dark matter might be something genuinely novel, something outside the categories of particles and interactions we have encountered before. Some theoretical physicists have suggested exactly this. The hidden valley concept imagines dark matter as part of a whole parallel sector of particles and forces, a dark sector that interacts with the visible sector only through gravity, and possibly through a few exotic portals. In this scenario, dark matter might have its own rich internal structure: dark atoms, dark chemistry, dark forces, all of it completely inaccessible to any detector we can build. The dark matter would be as complex as ordinary matter, just invisible to us. This is speculative, but it is not absurd. We have no a priori reason to think that the visible sector we inhabit, the one described by the Standard Model, is the only sector of physics. It might be one among many, with dark matter living in another sector that happens to interact with ours only gravitationally. If this is the case, then our understanding of dark matter will remain, permanently, an understanding of its gravitational effects, and nothing more. We will know where it is. We will know how much of it there is. We will know what it does to the structure of the universe. And we will know nothing of what it actually is. This is an extraordinary situation for science to contemplate. The dominant form of matter in the universe, possibly forever beyond the reach of anything except indirect gravitational inference. We would live in a universe we could describe, but not fully understand. We would know the shape of the dark matter's gravitational shadow, without ever seeing the object casting it. And yet that shadow is itself extraordinary. The cosmic web, revealed in gravitational lensing surveys. The rotation curves of 100,000 galaxies. The acoustic peaks of the cosmic microwave background. The bullet cluster, with its separated mass and gas. The dark matter deficient galaxies that show what happens when the scaffolding is stripped away. All of this is knowledge. Real, hard-won, extraordinary knowledge about something that cannot be directly touched. Perhaps this is enough. Perhaps knowing what dark matter does, knowing that it built the galaxies, shaped the cosmic web, made the universe what it is sufficient knowledge for a species that exists in the 5%. We cannot expect to know everything about the 27% just because we want to. The universe does not owe us that. But we will keep looking, because that is what physics does. And because, somewhere in the silence of the detectors, the flatness of the rotation curves, the gravitational arcs of distant clusters, the emptiness of the accelerator data, there is a whisper of something we have never encountered before. Something that has been here since the first second of the universe. Something that built everything. Something that is passing through you right now. We have not found it yet, but it is there. The galaxy you live in, the Milky Way, is embedded in a dark matter halo that you cannot see, cannot feel, and that extends into space hundreds of thousands of light years beyond the farthest visible star. It is, in the most literal sense, the largest structure you are part of, and virtually nothing is known about what it is made of. The Milky Way's visible disk of stars and gas, the spiral arms, the central bulge, the disk that you see as the Milky Way band crossing the night sky, is about 100,000 light-years in diameter. The thin disk is roughly 1,000 light-years thick. Within this disk, there are roughly 200 to 400 billion stars, enormous clouds of molecular gas from which new stars are forming. and vast regions of hot, ionized plasma left over from the deaths of old stars. But the visible disk is just the core of a much larger structure. The dark matter halo of the Milky Way has been measured using several techniques: the kinematics of globular clusters orbiting the galaxy, the escape velocity of stars in the outer disk, the dynamics of satellite dwarf galaxies, and the gravitational effects on the Magellanic Clouds. The results are consistent. The halo extends at least 600,000 light-years in every direction, and probably further. Some estimates put the halo radius at 1 million light-years. For comparison, the distance from Earth to the Andromeda Galaxy is about 2.5 million light-years. Our dark matter halo extends roughly to 1/3 of the way to our nearest large galactic neighbor. The total mass of the Milky Way's dark matter halo is estimated at roughly 1 to 2 trillion solar masses. The total mass of all the stars in the Milky Way is roughly 50 billion solar masses. The dark matter halo is therefore 20 to 40 times more massive than all the stars combined. Everything you can see when you look at the night sky, every star, every nebula, the entire visible band of the Milky Way, represents less than 5% of the galaxy's total mass. The density of dark matter in the solar neighborhood, at our distance of about 26,000 light-years from the galactic center, is estimated at roughly 0.3 to 0.4 GeV per cubic centimeter. This is the standard value used in direct detection experiments to calculate the expected rate of dark matter collisions with detector nuclei. It corresponds to roughly 1 proton mass equivalent of dark matter per cubic centimeter of space around you. If dark matter consists of WIMP-like particles with a mass of 100 GeV, 100 times the proton mass, then there are about 3,000 dark matter particles in each cubic meter of space around you right now. In your body, which has a volume of roughly 0.07 cubic meters, there are about 200 dark matter particles at any given moment. At the orbital speed of the solar system through the dark matter halo, about 220 kilometers per second, roughly 1 billion dark matter particles pass through each square centimeter of your body every second. These particles do not interact with the atoms in your body in any way you could detect. The scattering cross-section of WIMPs off ordinary matter is so small, smaller than the nucleus of an atom, that even in a ton of detector material, you might expect only a handful of interactions per year. In a human body, you would expect far less than 1 interaction in a lifetime. Dark matter passes through you as if you were not there. The halo is not stationary. It has a structure called the dark matter velocity distribution, the range and direction of velocities at which dark matter particles are moving in the halo. In the simplest model, called the standard halo model, the dark matter particles have a Maxwell-Boltzmann velocity distribution peaked at about 220 kilometers per second, with a maximum cutoff at around 550 kilometers per second. This distribution determines the spectrum of recoil energies that dark matter would produce in a detector. Faster particles produce higher energy recoils, and is one of the inputs to direct detection calculations. But the standard halo model is an approximation. Detailed simulations of galaxy formation show that the actual dark matter velocity distribution is more complex, with contributions from streams of dark matter that were deposited by the merger and tidal disruption of smaller halos over the Milky Way's history. One particularly significant stream, called the Gaia Sausage or Heracles, is a remnant of a major merger that occurred roughly 10 billion years ago, when a galaxy, roughly a quarter the size of the current Milky Way, was absorbed. This ancient merger scattered its dark matter throughout the Milky Way's halo in a distinctive pattern visible in the velocities of the merger's stellar remnants. The dark matter stream from this ancient merger passes through the solar neighborhood today, billions of years after the merger, at a characteristic velocity that is different from the bulk halo population. If dark matter is directly detectable, different stream populations would produce different recoil energy spectra, potentially distinguishable in a sufficiently sensitive detector. This is one example of how astronomical observations of the Milky Way's structure are directly informing the design and interpretation of dark matter detection experiments. The Milky Way's dark matter halo is also expected to have fine-grained structure, density fluctuations, streams, and clumps, on scales smaller than what current observations can resolve. These substructures are a prediction of cold, dark matter theory and carry information about the merger history of the galaxy. Future observations, particularly from the Gaia Space Telescope's precise stellar motion measurements and from the Vera Rubin Observatory's deep sky surveys, will reveal more of this substructure in the stellar populations that trace the dark matter. You live inside this halo. It built the galaxy you inhabit. Its gravity holds the galaxy together. Its ancient merger history is written in the velocities of the stars around you and in the dark matter streams flowing through this room. The galaxy is, more than anything else, a dark matter halo with a thin disk of visible material at its center. The stars are the decoration. The dark matter is the structure. The history of dark matter is in many ways a lesson in how science actually works. Not the clean narrative of hypothesis, test, confirmation, but the messier reality of observations dismissed, results ignored, careers built on conclusions that took decades to accept. Fritz Zwicky presented his dark matter calculation to the American Physical Society in 1933 in a paper titled Die Rotverschiebung von extragalaktischen Nebeln, the redshift of extragalactic nebulae. He was not a shy man. He described himself as a lone wolf and was known to his colleagues at Caltech as abrasive and difficult. He called his fellow astronomers spherical bastards. Bastards no matter which way you looked at them. His dark matter claim was treated as another example of Zwicky being provocative, possibly wrong, certainly not worth taking seriously. The reasons for dismissal were not entirely unreasonable. Astronomy in the 1930s lacked the precise instruments and statistical tools needed to make the mass measurements Zwicky needed with confidence. His calculation relied on estimating the mass of the Coma cluster from the average brightness of its galaxies, a method with significant uncertainties. The alternative explanation, that the galaxies were not actually gravitationally bound and were simply distributed along the line of sight by chance, seemed at least as plausible as Zwicky's invisible matter. For 2 decades, the observation was not followed up. World War II interrupted much of astronomy's development, and in the post-war era, the field's attention was focused on radio astronomy, the discovery of quasars and pulsars, and the development of the Big Bang model. Galaxy dynamics was not a fashionable subject. The first person to seriously revisit the problem, in the early 1960s, was Harvard astronomer Thornton Page. Page measured the masses of binary galaxies, pairs of galaxies orbiting each other, using the same orbital dynamics approach that Zwicky had used for the Coma cluster. He found the same problem. The visible mass was far too small to account for the observed orbital velocities. He suggested this might be evidence for missing mass. The observation was noted, debated, and again largely set aside. The preferred explanation was again that the systems were not gravitationally bound, or that the measurements had systematic errors. Then came Vera Rubin's rotation curves, which changed everything, not because they were the first evidence for dark matter, but because they were impossible to dismiss. Rotation curves are not subject to the projection uncertainties that plague cluster and binary galaxy studies. You are measuring the actual velocity of material at a known distance from the galactic center. The flat rotation curve is the data. It cannot be explained by projection effects or sampling bias. Either the outer stars are moving too fast for the visible mass, or our understanding of gravity is wrong on galactic scales. Rubin's data was too clean and too comprehensive to ignore. Her 1980 paper, Rotational Properties of 21C Galaxies with a large range of luminosities and radii from NGC 4605, R equals 4 kpc, to UGC 2885, R equals 122 kpc, presented rotation curves for 21 galaxies spanning a wide range of luminosities and sizes, all showing the same flat profile. The galactic center could not explain the outer velocities. Something additional had to be there. Even then, full acceptance took time. The 1970s and 1980s saw vigorous debate about whether modified gravity could explain the rotation curves without dark matter. Milgrom's MOND, proposed in 1983, was taken seriously by a significant minority of astronomers for decades. What finally tipped the balance was the accumulation of independent evidence: gravitational lensing, the cosmic microwave background, the large-scale structure of the universe, all converging on the same conclusion independently. By the mid-1990s, dark matter was consensus. By 2003, with the WMAP measurement of the CMB power spectrum providing a precise accounting of 23% dark matter, later refined to 27% by Planck, the case was airtight. Dark matter was a real, specific, measured component of the universe. Zwicky had been right in 1933. It took 70 years to be certain. The lesson of this history is uncomfortable. A correct observation, clearly stated, supported by a straightforward calculation, was ignored for decades because it implied something too strange. The scientific community's conservatism, its resistance to radical conclusions, delayed understanding of one of the most fundamental facts about the universe. This is not unique to dark matter. Similar patterns appear in the history of continental drift, the bacterial origin of ulcers, and the Big Bang itself. What dark matter's history also shows is that scientific truth is eventually self-correcting. The evidence accumulates. Independent lines converge. The strange becomes unavoidable. Zwicky was vindicated. Rubin was vindicated. The rotation curves are flat, and they stay flat no matter how many times they are measured. The one thing that has not yet happened, and might be the subject of another such delayed vindication decades from now, is the identification of what dark matter actually is. Somewhere, perhaps in a paper already published and not yet fully appreciated, perhaps in an experiment not yet conceived, is the identification of the dark matter particle. The history of science suggests that when the answer finally comes, it will seem obvious in retrospect. We are not there yet. The mystery gives reason for patience, and for the kind of confidence that comes from knowing that the data is real, the effects are measured, the invisible thing is genuinely there. We will find it, eventually. Dark matter's role in the universe does not end with the formation of galaxies and the sculpting of the cosmic web. It will continue to shape the universe's evolution for trillions of years to come. And the story of dark matter in the far future is in some ways darker than its story in the past. Right now, the universe is in a period of relative dynamism. Galaxies are forming stars. Galaxy clusters are growing by accreting material from the surrounding cosmic web. The Milky Way is on a collision course with the Andromeda Galaxy, expected to merge in approximately 4.5 billion years into a giant elliptical galaxy, sometimes called Milkomeda. That will itself be embedded in a merged dark matter halo of enormous scale. This merger is already underway in a slow-motion sense. The dark matter halos of the Milky Way and Andromeda are already overlapping. The outer edges of the two halos have been in contact for billions of years, exchanging dark matter particles through gravitational interactions. The stellar disks of the two galaxies, separated by 2.5 million light-years, will not begin to interact for another 3 to 4 billion years. But the dark matter is already beginning to merge. As the merger progresses over the next 10 billion years, the combined dark matter halo will settle into a new equilibrium configuration. The stars of both galaxies, tossed into chaotic orbits by the merger's tidal forces, will gradually settle into the smooth, featureless distribution characteristic of a giant elliptical galaxy. The gas, compressed by the merger, will trigger one final, massive burst of star formation before being expelled by the radiation from new stars and from the active galactic nuclei that the merger is expected to trigger. The local group, our collection of about 80 galaxies including the Milky Way, Andromeda, and dozens of dwarf galaxies, is itself gravitationally bound. The entire local group will eventually merge into a single massive galaxy, a giant elliptical sitting at the center of a single enormous dark matter halo. This process will take tens of billions of years. By the end of it, the local group will be a single object, containing the combined dark matter of all 80 current member galaxies. But beyond the local group, the universe's dark energy-driven expansion is carrying everything away. Galaxy clusters beyond our local supercluster are receding faster and faster. Within a few 100 billion years, they will cross our cosmological horizon and disappear from view. The local group will be left alone in an increasingly dark and empty universe. Within the local group's merged dark matter halo, the physics will continue for much longer. Dark matter particles will continue to orbit through the halo on timescales of billions of years, gradually exchanging energy through gravitational scattering. Some dark matter from the halo's outer regions will be slowly ejected into intergalactic space by these gravitational interactions. The same process that ejects stars from galaxies over long timescales. The halo will slowly evaporate from the outside in. Meanwhile, the stars within the merged galaxy will burn out one by one over trillions of years. Red dwarf stars, the longest-lived of all stellar types, will continue shining for several trillion years. As they burn out, they leave behind white dwarfs, dense, cooling remnants. Over many more trillions of years, these white dwarfs cool to black dwarfs, cold and dark. The merged galaxy will dim and darken, but the dark matter halo will persist, unaffected by the stellar evolution happening within it. Eventually, on timescales of 10 to the 30 power years, a number with 30 zeros, incomparably longer than the current age of the universe, even the stellar remnants will be disrupted by gravitational interactions within the old merged galaxy. Most will be ejected into intergalactic space. A few will fall into the central black hole. The visible component of the galaxy will effectively dissolve. The dark matter halo will outlast all of this. Unlike ordinary matter, Dark matter does not lose energy by radiation. It does not cool. It does not form cold remnants. The dark matter particles orbit in the halo on long, stable trajectories, exchanging energy gravitationally, only very slowly. The halo will still exist when the last white dwarf has faded to darkness, when the last black hole has evaporated via Hawking radiation, when ordinary matter itself has decayed. Dark matter may be the last surviving structure in the universe. When everything else is gone, stars burned out, black holes evaporated, ordinary matter decayed into radiation, the dark matter particles will still be orbiting, still interacting gravitationally, still forming a diffuse, cold, expanding halo in an otherwise empty universe. If dark matter is perfectly stable, if it does not decay on any timescale, then dark matter particles will persist through the heat death of the universe and into whatever comes after. This is a strange kind of immortality. The substance that cannot be seen, cannot be touched, cannot be detected even with the most sensitive instruments ever built. This substance will outlast everything else. It will be the final relic of a universe that once contained stars and galaxies and planets and life. Long after the last photon has been emitted and absorbed, long after the last black hole has exploded in a final burst of Hawking radiation, the dark matter will still be there, orbiting, cold, silent, unknown. The universe began in fire and light. It may end in darkness, a darkness made not of absence, but of something specific and real and invisible. A darkness made of the most abundant form of matter in the universe. A darkness that has been with us since the first second of creation, that built everything we can see, that holds the galaxies together right now, that is flowing through you this very moment. It has always been there. It will still be there when everything else is gone, and we still do not know what it is. But lying here, in a small pocket of ordinary matter, in a galaxy embedded in a dark matter halo, surrounded on all sides by something vast and invisible and fundamental, there is something fitting about not knowing. The universe has kept this secret for 13.8 billion years. It will keep it a while longer. The listening continues. The dark is patient, and so are we. Dark matter and dark energy are often discussed together, as if they were two aspects of the same mystery. They are not. They are completely different in their nature, their behavior, their effects on the universe, and the clues they provide about physics beyond what we know. Dark matter is a substance. It has mass. It clumps. It forms halos around galaxies and concentrations in galaxy clusters. It responded to the early universe's density fluctuations and collapsed under gravity to form the scaffolding on which all visible structure is built. It is distributed non-uniformly, densely in some regions, sparsely in others. And this non-uniform distribution is one of the primary things we measure when we study the large-scale structure of the universe. Dark energy is different in every respect. Dark energy is not a substance in the ordinary sense. It does not clump. It is uniformly distributed throughout space, the same density everywhere. It has a gravitationally repulsive effect. It causes space to expand rather than contract, and its density does not decrease as the universe expands. When a volume of space doubles in size, the dark matter and ordinary matter within it are diluted, the same number of particles occupying twice the volume, so the density halves. Dark energy, if it behaves like Einstein's cosmological constant, remains at the same density as the volume grows. More space means more dark energy, and more dark energy means faster expansion. This difference in behavior means that dark matter and dark energy dominated the universe at different times. In the early universe, dark matter dominated. The universe was small and dense, and dark matter's density was high enough to overwhelm dark energy's effects. Dark matter governed the formation of structure. About 5 billion years ago, as the universe expanded and dark matter's density fell below dark energy's roughly constant density, dark energy took over. Since then, the expansion has been accelerating. Dark matter holds things together. Dark energy tears things apart. Dark matter makes galaxies. Dark energy dissolves the connections between galaxies on the largest scales, slowly isolating galaxy clusters from each other and dooming the observable universe to eventual emptiness. They are, in a sense, opposing forces in the cosmic drama. Dark matter the architect, dark energy the entropy that undoes the architecture on the longest timescales. We are equally ignorant about both. We do not know what dark matter is. We do not know what dark energy is. The two greatest mysteries in cosmology, accounting together for 95% of the universe's mass energy content, are both completely unidentified. This should be a source of profound humility. The universe is made almost entirely of things we cannot explain, and we do not know when or whether that will change. What we do know is that the universe we live in, the 5% residue of ordinary matter, exists because of both of them. Dark matter built the structure. Dark energy calibrated the expansion. Together, they created the conditions for galaxies and stars and planets and life. Whatever they are, they conspired to produce us. And now we lie here, in the dark, surrounded by both of them, made of neither of them, trying to understand what they are. There is something both small and enormous about that situation. Small, because we are so tiny a fraction of what exists. Enormous, because we are the part that knows we are a fraction and wonders about the rest. The universe is mostly unknown, and the unknown is flowing through you right now. Tonight we followed a mystery that began with a Swiss astronomer staring at data in 1933 and noticing that the numbers did not add up. A mystery that was ignored for 40 years, confirmed by a woman who had been told astronomy was not for her, proved beyond doubt by a pair of galaxy clusters colliding in ways that showed their invisible mass, and their visible mass had been separated by the collision, and is now, after a century of searching, as deep as it has ever been. Dark matter makes up 27% of the universe. It built every galaxy that exists. It shaped the cosmic web that organizes everything on the largest scales. It is passing through your body right now, and we do not know what it is. We have not detected it in 40 years of increasingly sensitive experiments. The most sensitive WIMP detector ever built is operating right now in a mine in South Dakota, and it has not found anything. The world's most powerful particle accelerator has been smashing protons together for 15 years looking for new particles, and it has not found anything beyond the standard model. The galaxy rotation curves are as flat as they were in 1970 when Vera Rubin first measured them. Everything we know about it, we know from its gravitational effects. It pulls. That is all we know. It has mass, roughly 6 times more than all the normal matter in the universe. And it pulls. It does not shine, does not absorb light, does not emit radiation of any kind. It does not slow down when it passes through a galaxy cluster collision. It does not interact with anything in any direct detection experiment. It does not appear in any accelerator collision. It just pulls. It curved space-time around every galaxy and held it together. It built the halos that made galaxies possible. It laid down the scaffolding that the visible universe was built on top of. And then it stepped back and waited for the normal matter to arrive and do something interesting. The normal matter arrived. It formed stars. Stars made heavy elements. Heavy elements made planets. On at least one planet, chemistry became biology. Biology became consciousness. And consciousness started asking questions. One of the questions it asked was, what is most of the universe made of? And the answer still is, we do not know. Right now, lying here, the dark matter halo of the Milky Way extends hundreds of thousands of light years above you, below you, in every direction. Billions of dark matter particles flow through you every second, indifferent to your existence, invisible to every sense you possess. The substance that made the galaxy possible, that made the sun possible, that made the earth possible, that made you possible, is flowing through you right now, and you cannot feel it, and no one knows what it is. The universe is mostly something we cannot see, cannot touch, and cannot explain. We are floating in it. We are built on top of it. We owe our existence to it. And it remains, after 100 years of searching, entirely unknown. There is something fitting about lying in the dark, thinking about dark matter. The darkness around you, the darkness of a room at night, is a small and familiar thing. The darkness of dark matter is different. It is not the absence of light. It is the presence of something that light cannot touch. Something vast, something ancient, something that was there before the first star ever burned, shaping the universe in ways we are only beginning to understand. It is there right now, everywhere, in everything, invisible, and somewhere, in a mine in South Dakota, and a laboratory in Italy, and an observatory in Chile, experiments are listening for it, waiting for the first faint signal that would change everything. A signal that has not come in a century of listening, but that might come tomorrow. The universe keeps its secrets carefully, but it keeps building galaxies, and those galaxies keep making stars, and those stars keep making planets, and on those planets, minds keep asking the question, what is out there in the dark? We do not know yet, but we are listening. Sleep well.